In the last video, we explored the evolution of atomic theory, from classical atomic models to quantum mechanics, and the different energy levels and types of orbitals that electrons occupy. Today, we'll dive deeper into how electrons fill these orbitals within atoms, a concept known as electron configuration. Electron configuration describes how electrons are arranged in atoms' orbitals. This arrangement follows specific rules and principles, which help us understand the distribution of electrons across energy levels and orbitals within the atom. There are three fundamental rules that govern this configuration. First, we have the Aufbau principle. The term Aufbau comes from German, meaning building up. According to this principle, electrons fill orbitals starting from the lowest energy level to higher levels. In other words, each electron will occupy the most stable position available before moving to a higher energy level. The filling order of orbitals follows a specific sequence, from the lowest to the highest orbital. Instead of memorizing the series, we often use a handy method to derive it. First, we write numbers from 1 to 8 for representing energy levels. Then we add the S subshell to each of these numbers. Next, we add numbers from 2 to 7 for the P subshell, then from 3 to 6 for the D subshell, and finally, we write the F subshell using the numbers 4 and 5. We then draw diagonal arrows to determine the order in which orbitals will be filled. We can use diagrams and notation to visualize this configuration. We often represent orbitals by drawing boxes filled with arrows to indicate electrons. An arrow pointing up indicates that the electron is spinning in the upward direction, while an arrow pointing down indicates an electron with a downward spin. The second rule that we consider in electron configuration is Hund's rule, which states that when filling orbitals of the same type within a subshell, electrons will first occupy each orbital singly. Let's take, for example, the p subshell of the second shell. Electrons will first occupy each p orbital singly. The three orbitals will be filled one at a time before any pairing occurs. Only after each of these orbitals contains one electron will the electrons begin to pair up. The second electron will fill the first p orbital first, followed by the second p orbital and the third. This approach minimizes electron-electron repulsion, as electrons are placed in separate orbitals rather than sharing them immediately. As a result, this arrangement leads to a more stable electron configuration. The third and final rule of filling orbitals is the Pauli exclusion principle. This principle states that no two electrons in an atom can have the same set of quantum numbers. This means that when filling electrons, the two electrons in each orbital must have opposite spin directions. This is only possible by filling all the single electrons in the upward direction and then pairing them with electrons in the downward direction. Let's now try to represent the electron configuration for the sodium atom, which has 11 electrons. We start by filling electrons in orbitals of the lowest energy level in the electron configuration series, which is the s orbital of the first energy level. It can hold two electrons. The first electron points up and the second points down. We then fill the s orbital of the second energy level with two electrons in the same way. Next, we fill the p orbitals one at a time, all pointed up, and then we pair them with electrons in the downward direction. That makes 10 electrons in total. We add the last electron in the s orbital of the third shell, which completes the electron configuration for the sodium atom. We often use this specific notation to represent electrons in a specific orbital, where n represents the energy level, L is the subshell type, and I is the number of electrons existing in that subshell. For example, a notation of 3p to the power 5 means there are 5 electrons in the p subshell of the third shell. For sodium, we write its electron configuration as. This simple representation helps us visualize the distribution of electrons more easily. If we consider another atom such as iodine, which has 53 electrons, the full electron configuration is quite lengthy and can become tedious to write out completely. To simplify this, we use a shorter way by writing the electron configuration starting with the nearest noble gas that comes before iodine, which is krypton. Krypton has 36 electrons. We count 36 electrons in the series, and we replace them with krypton in between brackets. Then we resume the electron configuration from this point till we reach the 53rd electron, which lands at the 5th p subshell. And this is how we write the electron configuration for the iodine atom. To summarize, electron configuration describes how electrons are arranged in atoms, using three key principles. By understanding these principles, we can predict and represent the electron configuration of any atom. Thank you for watching, and stay tuned for our next video.